Hello, and welcome to my video series of algorithms. This is part 1 of Module 5, Divide and Conquer Algorithms. In this video, we will provide a brief introduction to this algorithm design principle. In many cases, where we face a challenging problem, we break it down into smaller, more manageable parts and solve them one by one. We hope that by solving these smaller problems, we can combine their solutions to solve the original problem. For example, imagine that you are the CEO of a company aiming to launch a new cell phone in the market. Its success depends on various aspects like sales, marketing, and engineering. Of course, handling all of these tasks alone would be overwhelming. Therefore, you decide to hire experts in each field. You might bring on a VP for sales, another for marketing, and one for engineering. By delegating these tasks to specialists, you can ensure each area is managed effectively, ultimately contributing to the overall success of the project. Now, consider what you need to do in this process. First, you need to divide the overall task of achieving business success into smaller tasks, such as marketing success and engineering success. This step is known as the divide step. The smaller tasks are referred to as the subproblems of the original problem. The next step is for the VPs to complete their assigned smaller tasks. From the CEO's perspective, you assume that these tasks are being accomplished in this step. Consequently, we refer to this step as the conquer step. It is important to know that you, as the CEO, don't usually focus on the specific details of how the tasks are being accomplished. You usually treat this step as a black box. Once the tasks are accomplished, the VPs will report their results to you. You will then gather all the information to create the optimal business plan. For example, you might need to consider the cost and technical specifications reported by the VP of Engineering, as well as the market needs and affordability reported by the VP of Marketing. Since different pieces of information are combined in this step, we refer to it as the merge step. The entire process can be summarized in 3 main steps. First, the CEO divides the large problem into smaller subproblems and assigns them to the VPs. Second, the VPs complete their assigned tasks. Third, the CEO collects the reports and determines the optimal solution for the larger problem. In short, this is the divide, conquer, merge paradigm. Note that this process can be performed recursively. While the CEO does not need to know the details of how the VPs accomplish their tasks, the VPs themselves must develop concrete plans. The VPs can use the same divide, conquer, merge paradigm to complete their tasks. For example, the VP engineering can divide the larger problem of creating a good phone into subproblems like making a good camera, developing a reliable wireless communication chip, and designing a robust operating system, etc. When we combine the CEO's perspective and the VP's perspectives, we can create a tree-like hierarchy that represents the divide, conquer, merge paradigm. Of course, like all recursive processes, we also need to design exit plans for the divide, conquer, merge paradigm. When the tasks become very simple, such as pasting stickers or tightening screws, the people assigned to this task can complete them directly. Here is the pseudocode for the divide, conquer, merge paradigm. Line 2 specifies the exit plan for the recursion. Line 3 divides the larger problem into a set of smaller subproblems. Lines 5 to 8 solve each of the smaller subproblems recursively. Line 9 merges the solutions of the smaller subproblems and constructs a solution to the larger problem. As you might have guessed, the divide, conquer, merge paradigm is formally known as divide and conquer. However, when designing such algorithms, the focus should be on the divide and merge steps, rather than the conquer step. This is because the conquer step is achieved through recursive calls, which are treated like black boxes. In addition to its applications in real life, we can also solve many computational problems using divide and conquer. For example, we can compute the Fibonacci series using a divide and conquer approach. Originally, the Fibonacci series was used to model rabbit population growth in the wild. Mathematically, the nth number in the series is the sum of the n-1th and the n-2th numbers. The base cases are that the first and second numbers are both 1. The first few elements in the series are 1, 1, 2, 3, 5, and so on. To compute the Fibonacci series using divide and conquer, we can break the problem of computing the nth number as subproblems of computing the n-1th and n-2th numbers. We can further break the problem of computing the n-1th number as subproblems of computing the n-2th and n-3th numbers. We can recursively divide these subproblems until we reach the base cases, where the solutions are directly computed and returned. Here is the pseudocode for computing the Fibonacci series using divide and conquer. Line 2 describes how to handle the base cases. Line 3 combines both the divide and merge steps, as both are simple and straightforward. Now, you might wonder, what's so exciting about divide and conquer algorithms? Isn't it just another recursive algorithm? Well, the divide and conquer algorithm is not ideal for computing the Fibonacci series. This is because we cannot save computation by dividing larger problems into smaller subproblems in this specific case. To understand why, consider that it takes one addition to compute the 100th number in this series, and it also takes one addition to compute the third number in the series. There is no difference in the amount of computation needed between solving larger and smaller problems. On a separate note, the Fibonacci series can be computed much faster using dynamic programming, which we will discuss in later modules. To illustrate another important application of divide and conquer in making algorithms run faster, let's recall the merge sort algorithm. We discussed the merge sort algorithm in part 7 of module 1. I will put the link in the description so you can review it if needed. The merge sort algorithm is a sorting algorithm devised under the divide and conquer paradigm. It first divides the input into two equal sized subsets, then recursively sorts each subset, and finally combines the two sorted lists into one. Here is the pseudocode for the merge sort algorithm. Line 2 describes the base case. Line 3 describes the divide step. Lines 4 to 5 describe the conquer step, where we sort the subsets by recursively calling the merge sort function itself. Finally, line 6 uses the function merge to combine the two sorted lists into one. Specifically, the merge function uses two pointers to traverse the two sorted lists to be merged. Initially, the pointer p1 points to the first element of the first list, and p2 points to the first element of the second list. It then compares the two elements being pointed and copies the smaller one to the output list. For example, the smallest element in the first sorted list is 4, and the smallest in the second list is 1. Since both lists are sorted, 1 is the smallest element overall. Therefore, we place 1 as the first element on the merged list. After that, we move the pointer p2 to the next element and iteratively perform the above steps until all elements are placed into the merged list. The merge process takes O(n) time, where n is the total number of elements. Now, let's analyze the merge sort algorithm and determine whether it can save computation using divide and conquer. Recall that simple sorting algorithms run in passes, determining the ranking of one element per pass. In each pass, they need to make comparisons with all remaining elements. For example, if we are sorting 10 elements using selection sort, we will make 9 comparisons in the first pass to identify the smallest element. In the second pass, we then make 8 comparisons among the remaining elements to identify the second smallest element, and so on. It is easy to see that the total number of comparisons is n times n-1 divided by 2, which also applies to other similar algorithms like bubble sort and insertion sort. In this case, if we directly sort the entire set, the time we need is n times n-1 divided by 2 times tcomp, where tcomp is the amount of time needed for each comparison. On the other hand, consider using merge sort algorithm. The divide step should take O(n) time, since we only need to copy the input into 2 separate lists. Hence, the divide step would take n times tdiff time, where tdiff is the amount of time needed to copy an element. For the conquer step, the time for sorting one subset becomes n/2 times n/2 minus 1 divided by 2 times tcomp, where we replace n in the original formula with n/2, since each subset contains half of the elements. For sorting 2 subsets, we multiply the formula by 2, getting n times n/2 minus 1 divided by 2 times tcomp, which is approximately n times n-1 divided by 4 when n becomes large. Finally, for the merge step, we show that it takes linear time n times tmerge, where tmerge is the amount of time needed for merging one element. Adding the time together, we get n times tdiff plus tmerge plus n times n-1 divided by 4 times tcomp. Hence, the difference between the time needed by direct sorting and that needed by merge sort is n times n-1 divided by 4 times tcomp minus n times tdiff plus tmerge. Note that the time terms tcomp, tdiff, and tmerge are all constants, and the only variable is the input size, n. Clearly, the difference will become positive when n grows large, because the first term grows quadratically with n, while the second term grows linearly. This means that the time needed for direct sorting is more than that for merge sort. In other words, the divide and conquer strategy saves computation in this case. Indeed, the merge sort algorithm runs in O(n) log n time, which is faster than the O(n) squared time complexity of the other simple sorting algorithms, like selection sort, insertion sort, and bubble sort. The details of the time analysis was discussed in Part 7 of Module 1. Please see the link below if necessary. From the merge sort example, we can see that divide and conquer is not only a general problem-solving strategy, but also an important technique for speeding up algorithms. As a general problem-solving technique, it needs to consider all possibilities when defining the subproblems. Hence, we can directly accept correctness in most cases. On the other hand, as a speed-up technique, we need more detailed analysis of the time complexity for divide and conquer algorithms. Note that the treatment for divide and conquer algorithms is opposite to greedy algorithms, where we care more about their correctness since they usually don't directly consider all possibilities. Finally, as an overview of the content in this module, we will discuss various computational problems, including counting inversions, integer multiplication, matrix multiplication, the closest pair of points, R-select, and fast Fourier transform. We will also discuss the master's theorem for analyzing the time complexity of divide and conquer algorithms. Thank you for watching, and see you next time.